Hi and welcome again to another chemistry lesson. We're looking at haloalkanes properties and reactions, and in this lesson we're going to look at some haloalkane reactions. The first one I want to look at is how do we actually create a haloalkane, and the process is fairly easy. What we'll do is we'll start with an alkene. Okay, well, one way of doing it is starting with an alkene, then to the alkene we add a halogen. Okay, a halogen. Now it's important that we start with an alkene which is not saturated. It's an unsaturated hydrocarbon, and therefore some of the bonds can be replaced with other bonds. Okay, so that is important, and this produces a haloalkane. I'll look at an example and it will make a lot of sense in just a minute. Just what do we call this process of adding a halogen to an alkene? Well, it's this very complicated name, halogenation. Okay, halogenation. In other words, halogenation is when I add a halogen to an alkene. You might recall in a previous video that we looked at hydrogenation. That's when we added a hydrogen to an unsaturated alkene, producing a saturated alkane. Okay, so not complicated at all so far. So let's look at an example. So if I were to take an alkene like propene, okay, so if we took propene, that is C double bond to C, single bond to another C, and there I'm not going to add in my hydrogens. Okay, but there's my propene. Well, let me add in my hydrogens just so that you know that you are supposed to as well. So there's my hydrogens, and to this I'm going to add something like chlorine. Okay, well, let's go for bromine. Bromine. Okay, this is bromine. So propene is C3H. 1, 2, 3, 4, 5, 3, 6. There we go. Plus bromine, Br2, and this produces, and I'll show you now what it produces. So what is going to happen in this reaction is that this double bond, it's a little bit more complicated than that, but you can understand it like this for now. This double bond is broken up, okay, and so now we've got one valence electron here and one valence electron there. So one of these double bonds are broken up, and the one is going to share with the one bromine has got 1, 2, 3, 4, 5, 6, 7. The other one has 1, 2, 3, 4, 5, 6, 7 valence electrons, and since they are sharing these two, what's going to happen is instead of sharing with one another, this one is going to share his valence electron with this one, and the other one is going to share his valence electron with that one. Okay, so it's going to end up producing C carbon single bonded to carbon, single bonded to carbon, and we'll have a bromine here, hydrogen here, and then here we will have another bromine. Now, for the purpose of this course, it's not necessary that you have them on opposite sides, but it is basically how these ones most of the time will produce on either side. It would be this asymmetric pattern. Okay, so this one is called 2-1,2 dibromo, dibromo propane. Okay, that's going to be this one's name. Why? Because on the first, second, third, on the first and the second carbon, he's got a bromine. Okay, and because there's two, we use the prefix di. Okay, this is called halogenation. Okay, not very complicated. The reaction conditions is what do you need to know about how this reaction takes place? Well, it is a very, very complicated process. It's really not as easy as this. But basically, all you need to know is that the important part for this course is that bromine is added to alkene. Okay, so that's all you need to know, is that we add bromine to alkene, not the other way around. So the halogen is added to the alkene. That's the reaction condition. The next one we are going to look at is called, well, let me show you first. The next one, we're going to take an alkene, and to this alkene we are going to add a hydrogen halide. Okay, now that seems like a, oh sorry, not like that, hydrogen halide, and that is going to produce a haloalkane. Now, you're just asking me, what on earth is a hydrogen halide? Well, you remember that when our halogens react, something like bromine, chlorine, they become bromide and chloride. Okay, so when we do have hydrogen combined with a halogen, it's called a hydrogen halide. Instead of hydrogen halogen, it's a hydrogen halide. So it's not very difficult. This is simply a hydrogen combined with a halogen. Okay, one of the group 7 elements. So if we look at an alkene that has some double bond somewhere, okay, and in the previous one we saw how it used to be X bonded to X. Now it's just a hydrogen bonded to X. The only difference now is when this bond breaks up, instead of it getting a halogen on the one valence electron and a halogen on the other one, this time it will just get a hydrogen and a halogen. Okay, so before I go any further, what is this process called? Well, again, a very simple name. It's the previous was halogenation. This one gets a hydrogen, so it's hydrohalogenation. Hydrohalogenation. Again, very simple name, referring to adding a hydrogen and a halogen to an alkene. Okay, so let's look at an example of that. Let's take a different example this time. Let's take a butene. Is my butene. This time I'm not going to put in the actually, let me keep the double bond on the end so that I can show you something. Okay, there we go. I'm not going to, oh well, let me do it. For your sake, I'll still add the hydrogens. Okay, so add all our hydrogens. Excellent. And now to this hydrogen, we are going to add a hydrogen halide. Okay, let's go for chlorine. Hydrochloric. This is called hydrochloric acid. Later on, when we do acids and bases, you'll understand why this is an acid. But for now, you can just see it as hydrogen chloride. Okay, so there's hydrogen chloride, and this produces, well, what will this produce? As I had said already, what is going to happen is that one of the bonds in this double bond is kind of going to break up. So we're going to have a valence electron here and a valence electron there. And now the question is just, the question is which valence electron will it attach itself to? Okay. In other words, will the hydrogen attach to the second carbon or to the first carbon? Or actually, probably our curiosity is more about where will the chlorine go. Okay, will it attach itself to the first chlorine, or the first carbon, or the second carbon? And even though we can look at that, it is easier to remember that the hydrogen is the one that's going to choose its position. The hydrogen will choose the carbon with the most hydrogens already. So it's almost like he's going with the more popular group. Okay, so he's going to go with the hydrogens where there's or the carbon where there's already 2 instead of just 1 carbon. So in other words, this hydrogen will go to the first carbon, and the chlorine will go to the second carbon. Okay, so what we'll end up having is 4 carbons, single bonded. The first carbon will get the extra hydrogen. The second carbon that already has 1 hydrogen will now get a chlorine, and the others will obviously stay unaffected. Okay, what is this one called? Remember, we must number our chain so that the chlorine would be at the closest end. So this would be 1, 2, 3, 4. So this is 4 carbon chain. That makes it a butane. Okay, there is a chlorine. There's only a single chlorine, so it's chlorobutane, and that chlorine is on the second carbon, so it's 2-chlorobutane. That is the product of this reaction. Okay, reaction conditions. In this time, the important reaction condition is that, and I'm going to write it down, so important it is. Okay, no water present. Okay, there can't be any water present in this reaction, so in other words, you can't use water as a solvent or anything like that. And the reason why is because when we add alkenes to water, it is much more reactive to the water, so it's much more likely to react to water than to a halogen, to the halogen halide, and then it will produce an alcohol, which is the next topic we will look at. It will produce an alcohol instead of a haloalkane that we're desiring. So that's the only condition that we're going to look at. Again, this process is much more complicated than just adding hydrochloric acid and the alkene together somehow. It's a whole process, but the important reaction condition to understand here is that no water must be present.